Welcome to the Space Telescope Public Lecture Series. Tonight, Stephan's Quintet, a multi-wavelength exploration by Frank Summers of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers, and I would love to thank my wonderful tech team, Thomas Marufu and Grant Justice, who bring you these events online every month. And I will note that the Space Telescope Public Lecture Series will continue to be online only throughout 2023. Our upcoming talks include on August 1st, a very special celebration, Webb Space Telescope, the First Year of Science by Macarena Garcia Marin, both Space Telescope Science Institute and the European Space Agency. If you don't remember, it was almost 1 year ago, actually it's 1 year ago tomorrow, that Webb released its first science results, and we're going to have a special talk in August to commemorate that first year of science. In September, on September 5th, Alexandra Hamowitz of the Space Telescope Science Institute will discuss the interstellar medium. She hasn't given me an exact title, but the interstellar medium, that's the stuff in between the stars and the galaxy. And it's an amazingly complex topic. You sort of think, oh, there's nothing between the stars. No. There's really cool stuff in between the stars. And she'll tell you all about that. On October 3rd, Nimisha Kumari is giving a talk. And again, I have not gotten an exact title. I haven't even gotten a topic for it, but I'm sure I will be able to get it in the next couple weeks and have it for you next month. When that title is known, it will appear on the Public Lecture Series website, www.stsci.edu/public-lectures. There you can see we have our list of things, including in the lower left, you can both the Space Telescope Science Institute webcast as well as our YouTube playlist. In the lower right is where you can sign up for our monthly emails. That's basically 2, maybe 3 emails a month reminding you of upcoming and when webcasts are posted. We have the list of the lectures, and for each lectures, And for each lecture, we have the information about it, the description, as well as links to the webcast after it has broadcast. For email, as I said, sign up at the website for the announcements. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. That will give you the new video notices and the reminders of live events such as this. And if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Now, at Space Telescope, we run the social media for the Hubble Space Telescope, for the Webb Space Telescope, and we have our own STSCI social media on Facebook, Twitter, YouTube, and Instagram. And I myself do a tiny little bit of social media on Facebook and Twitter as Dr. Frank Summers. The news from the universe for July 2023. And since I am the speaker tonight, I only have one story for you, but it's a really cool story. And it's about the James Webb Space Telescope examining the distant/early universe. We're going to start out not with Webb, but with Hubble. This image you see in the lower left corner here, that is the Hubble Ultra Deep Field, okay? A collection of about 10,000 galaxies. And as you can see, it's just a 2D image. That's what we release to the public. But we as astronomy buffs know that those galaxies are all at different distances. So if I put this into motion, this is from a visualization that we released a few years ago, we can stretch out those galaxies of the Hubble Ultra Deep Field and put them at their correct relative distances across the universe. So these galaxies that are in a 2D image actually stretch across the 3D universe. And here they go out to about 12 billion light years in this data set. And so they stretch out across the universe, but they also stretch out across time, because a galaxy that is 5 billion light years away is seen as it was 5 billion years ago. So the galaxies that you see farther and farther into space are seeing them as they were farther and farther back in time. As I love to say, the phrase, out in space equals back in time. And JWST, the Webb Space Telescope, is pushing that even further. And with surveys such as this is the JADE survey, the JWST Advanced Deep Extragalactic Survey. I gotta say, astronomers have a really intense time coming up with cool acronyms. All right, and they came up with the acronym JADES. All right, and this one contains 45,000 galaxies in this image. You can't see them. You know why? Because this is 100 image, okay? And on your computer screen, you can't see anywhere near that many. So what I'm going to do is I'm going to zoom into this region, which is just 2 megapixels. This is a 1920 by 1080 cutout of the image, and show you all the galaxy goodness. And, whoops, wrong button. There you go. That is some galaxy goodness. Okay, lots and lots and lots of galaxies. All right, and the thing is, what the JADE survey folks have found is that there are more galaxies than they expected. Okay, we have an idea of how galaxies shine in the infrared and how that should be, but what they're finding is that there are more galaxies than they expected, and in particular, more galaxies at very high redshifts. So they're getting a lot of the many more distant galaxies than they expect. And one of the reasons for it is that they are also finding that the star formation in these very distant, very early galaxies is stronger than they expected. So if there are more stars forming in these distant galaxies, well, then they're brighter than they expected, and therefore they will see more of them. And so this is just sort of, you know, the preliminary results of it. After studying their data for a while, they still have a lot more to do, and as the data is all now collected, they can do much more detailed studies. But the results are really exciting. Now, that's just one survey. There is a second survey called the SEERS survey, and this is called the Cosmic Evolution Early Release Science Survey. Yes, astronomers love their acronyms on their surveys. And instead of going deep into one field like the JADES team did, this team spread their things out to try and look at how many objects they could see with, you know, sort of a medium deep level survey. Okay, and so you can see it's got this funky pattern because they wanted to maximize the area they were able to cover with 10 different observations that gave them 20 fields to study. But we're not going to go across the entire 100,000 objects in this entire field. We're going to go into this region here, which is one of the first ones they found. And here you can start to see, yet again, there's a lot of galaxies deep across the universe being discovered by Webb. What's interesting here is that they've got about 10,000 objects in this image, about 5,000 of which they were able to get good redshifts for, redshifts being the measurement that we use to proxy for distance. And I'm not going to talk about all 10,000 or all 5,000 of those objects. I'm really just going to talk about one, that one right there. Yeah, I know you can't see it, but I'll show it to you in detail in just a second. This galaxy was very quickly identified as possibly being at a redshift 12. Okay, what does redshift 12 mean? It means that it's being seen at about 13 to 13.5 billion years ago. The universe, the Big Bang, was about 13.8 billion years ago. So we're talking about the first half a billion years after the Big Bang, all right? This is kind of cool. All right, so how do we know this? Well, that's illustrated in this set of images across the bottom. You will notice that in the leftmost image, you cannot see the galaxy. This is visible light. I think these are actually the visible light images from Hubble. And then you go to the F115 and F150. These are 1 and 1.5 micron observed by JWST. Again, you don't see anything. The first place where you can see it is in the 2 micron image here in the center, and then a little bit in the 2.7 and the 3.5 micron images with JWST. So the fact that you could only see the galaxy beyond 2 microns means that all of its light has been redshifted beyond out to those infrared wavelengths. Even the ultraviolet light from the star formation that they're seeing in these galaxies has been shifted across the visible and into the infrared. That is how you estimate the redshift at redshift 12. Fortunately, they were able to go back with spectroscopy and really pin down the redshift, and they were right. It is not redshift 12, but it's a redshift of 11.41, one of the highest redshift galaxies known, right? And with the results of the Sears group and the Jades group, we're going to get a whole family of objects out beyond redshift 11. All right. The other really cool thing that they did is they gave their data to us here at the Space Telescope Science Institute, and my team and I worked together to create a visualization of flying into that image and examining this galaxy, which they nicknamed Maisie's Galaxy. So here's our visualization of a flight to Maisie's Galaxy. All right, so in summary, through surveys like Jades and Sears, the James Webb Space Telescope is peering to the very distant universe, which is also the very early universe. It's looking at these very early galaxies and studying the first billion years, even the first half billion years of the universe and how these galaxies develop. And I will say, yet again, this is just the tip of the iceberg. This is the beginning of these really exciting results that we have been looking forward to with, getting from the James Webb Space Telescope for quite some time. Okay, on to our featured speaker. Our featured speaker tonight is me. I am the speaker, and every now and then I take over the reins and not only do the introduction and play host, but I also do the speaker. Let's see, what can I tell you? I always like to try and tell you something about myself that you haven't heard before. So let's see. Oh, I know a question I usually get. A question I often get is, when you were growing up, did you know you wanted to be an astronomer? And the answer is no. If you asked me in 4th grade what I wanted to be, I would have said I wanted to be a baseball pitcher. I was really into baseball at the time. I was unfortunately afflicted with a love for the Boston Red Sox. Back in those days, the Red Sox had not won a World Series in like 70, 80 years. It was the curse of the Bambino, which finally got lifted after the turn of the century, but not until I was fully well grown up. I didn't actually turn on to astronomy until much later. I grew up loving to solve puzzles, And to me, math puzzles were really cool. And I did my undergraduate degree in physics because that's where the coolest math puzzles were. I love word problems, okay? And physics was a great place to solve word problems. And then after I did my undergraduate work in physics, I moved to astronomy because astronomy had the really cool puzzles because you had to just examine the light that's coming down from the universe and figure it out. Okay, so that's how I became an astronomer. It wasn't really a particular path. It's math and puzzles to physics to astronomy. And it's probably good I wasn't a baseball pitcher because my shoulder comes out of socket. I got loose tendons. So, if I tried to do that, I would have failed. All right. Okay, so let's get on. Let's share my screen. And get on with my talk. Okay. My talk tonight, Stephan's Quintet, a multi-wavelength exploration. And I probably haven't said this before, but my official title at Space Telescope Science Institute is Principal Visualization Scientist here. Yeah, you guys know me as the host of the PLS, but that's what they call me. What I like to call myself, there we go. What I like to call myself is an astrophysicist, just because it's a cool name of an astronomer who gets paid to make movies. And tonight we're going to talk about galaxies. And when you think of a galaxy, you probably think of a spiral galaxy like this, a Messier 101. Gorgeous, wonderful, spiral galaxies. They're everybody's favorite. But galaxies also occur in other shapes. They have elliptical galaxies. This is a relatively large elliptical galaxy. And they're fuzzy and warpy and oblong. And they really don't have an edge sometimes. Like this one sort of stretches out all the way to the edge of this image. That's one really cool thing about elliptical galaxies is they're starlight fades off so slowly. It's a logarithmic fade off and such, and it really, there's not a good strong edge to them. Galaxies also occur in shapes that are called irregular, which means that they don't have any particularly well-defined shape. And there are a lot of these irregular galaxies. Many of them are dwarf galaxies, okay, because they're too small for the gravity to pull them into a regular shape just yet. But some of the galaxies that people think of as irregular, or used to think of as irregular, are galaxies that look like this. And you can see, wow, there's stuff going in strange directions. There's not a spiral. It's not elliptical. Is it an irregular? No. It's actually something that we call a peculiar galaxy because it's not one galaxy. It's actually two galaxies. This is two galaxies having a collision. And these are two galaxies that are interacting, and then the pieces of the galaxies fly off in strange directions. All right. And I guess if you think of two galaxies having a collision, you think of something like this. This, you can see the two galaxies have flown past each other. They pulled out these big, long tidal streamers on them. And they've got these telltale shapes of these galaxies' interactions. And the name peculiar galaxies comes from the ARP Atlas of Peculiar Galaxies. And what he did is he cataloged all sorts of things that basically were galaxy interactions. Two galaxies that are pulled out and had strange things on them. He called them peculiar, and the name kind of stuck. All right? And so galaxy interactions can have another effect. This is a visualization of a simulation of our Milky Way galaxy and the Andromeda galaxy starting about 1.75 billion years from now. And when galaxies collide, they will at first start and they will pull out these big tidal tails, but eventually they come back together and settle. So in about 4 billion years, the Milky Way and Andromeda, well, they're going to smash through one another. And you can see those big tidal tails getting stretched out, all right? But gravity is one way. It's a one-way street. Those two are eventually going to come back together, mix it up, crash in, and then about 6 billion years from now, maybe 7 billion years, what's it going to look like? Those two spiral galaxies are going to look like an elliptical galaxy. And that is one of the important results from computer simulations over the past few decades, is that when galaxies collide, they tend to form elliptical galaxies. That you can take spiral galaxies, crash them together, transform them into an elliptical galaxy, and that we think that that is probably the dominant way that elliptical galaxies form, which is via mergers. Okay? All right, so we talked about galaxies and pairs of galaxies and seeing what can happen to pairs of galaxies which they come back to one galaxy. But you may also know about clusters of galaxies. This is the galaxy cluster SMACS 0723, observed by the Webb Space Telescope. And there are tons and tons and tons of galaxies, probably a few thousand galaxies in this. This is one of the largest galaxy clusters that we know of in the universe. It's so large that gravitational lensing occurs, but that's a totally different talk, okay? So I'm not going to get into that here. But there are galaxies can congregate into hundreds or thousands of them in these clusters. But what we really want to talk about today is sort of the in-between stage. Is there an in-between stage between like 1 and 2 and these tons of things? Of course there is, otherwise I wouldn't bring it up. And they're called groups of galaxies. This one is called Hickson Compact Group 40. And it is a collection of 5 galaxies, as you can see here. And these 5 galaxies are very close together on the sky. That's what makes them a compact group, that are close together on the sky. And these are sometimes physical associations where the galaxies are actually at the same place. Sometimes they're just sort of a line of sight thing. They're strung along this linear feature toward us so that we see them as being very close to the sky, but they're relatively well separated. And there are about 100 of these. Paul Hickson created a catalog of about 100 of these compact groups. But there is one that is most famous. And it actually was the first compact group discovered. And it actually is the most studied of it. But that's not the reason it's the most famous. It's the most famous galaxy group because it's been in the movies. Yep. At the beginning of the movie, It's a Wonderful Life, the angels are talking to one another, and Angel Joseph is a galaxy, and the senior angel is another galaxy. These are galaxies within Hickson Compact Group 92. Yes, yes. It's a Wonderful Life starts with angels talking to one another, which are actually part of a galaxy group. And Hickson Compact Group 92 is better known as Stephan's Quintet. So here is a little better image of Stephan's Quintet. All right, and there are 5 galaxies here. Let me point them out to you. All right, up here, down here in the lower right, we have NGC 7317. Here in the middle, we have MGC 7318A on the right and 18B on the left. In the upper left, we have NGC 7319, and below that, we have NGC 7320. I'm sorry they don't have any particular poetic names. These are just the catalog numbers in the NGC catalog, okay? And so one of the things, as I said, with the compact group is, how do we know that these are actually associated with another in distance, or whether they're strung out along the line of sight? Well, we do something, we measure their redshifts. And let me explain that to you in a little more detail, just to make sure you have that underthing. So, part 1 in discussion of redshift is cosmological redshift, okay? Or just simply the expansion redshift, the redshift that's due to the expansion of the universe. So if you look at this drawing here, we have a bunch of galaxies and they're on a grid. And that grid is supposed to represent the space-time of the universe, okay? And that grid is going to expand. And so after some time, that grid has expanded and the galaxies have been carried further apart. Now note, it's the grid that gets bigger, not the galaxies. The galaxies don't get bigger. The galaxies are sort of just carried along by the grid. The galaxies don't have to be moving. They can be perfectly stationary. The grid carries them apart, and every galaxy sees every other galaxy moving away from it, okay? That is expansion redshift. And the further point is that the further away the galaxy is, the faster it appears to be moving away from it. Now, this isn't any real physical motion. This is just motion, apparent motion, due to the expansion of the universe. And this is what leads to the very famous Hubble's law, that the redshift of a galaxy, cosmological redshift of a galaxy, is equal to the distance times this parameter, h, which is the Hubble parameter. Since Edwin Hubble came up with the law, he gets to have his name on the parameter. All right, and this Hubble parameter, for those of you who care, is about 70 kilometers per second per megaparsec. And if you don't understand that, don't worry about it. That's just something for those who really want to know. But the most important point to remember here is that with expansion redshift, it's proportional to distance. So if you measure the redshift to a galaxy, the larger the redshift, the further away it would be, just due to expansion. Okay? There will be a part 2, so we'll get back to that in a bit. So if we get back to Stephan's quintet, and we have these 5 galaxies in Stephan's quintet, here are their measured redshifts. Okay? And we can go back to Sesame Street and say one of these things is not like the other. Which one is different? Well, we've got 4 galaxies that are around 6,000 kilometers per second in redshift speed, and 1 galaxy that's around 800 kilometers per second. So if the redshift is proportional to distance, then NGC 7320 is really close to us compared to the other galaxies, okay? The other 4 galaxies are much further away. They appear to be physically associated with one another, while NGC 7320 is just a foreground galaxy that happens to be along the same path. I find that really cool because, 7320 looks to be about the same size as them. And you'd think if these guys are 6 times farther away, they should be a lot smaller. Well, not necessarily. It's really kind of cool that it looks about the same, but it's 1/6 the distance of the other galaxies. So Stephan's quintet is actually physically a quartet, except if you do a slightly wider field image. Then you discover this other galaxy over here, NGC 7320c, which was not part of the Stephan's quintet discovered by Edouard Stephan, or included in Hickson Compact Group 92 by Paul Hickson, but it is about the same redshift as them, and so could be physically associated with them, all right? And so if we look at the redshift plot again, and we add in 7320c, we can see that it's about out of the same distance, okay? So let's ignore 7320 for right now. We're going to get rid of it, and let's look at this plot with just the other 5 galaxies, okay? So here comes something interesting, is that we have 3 of them around 6,600 kilometers per second in redshift distance, and 2 of them around 5,900 in redshift distance. So there's a little separation between the 3 in what look like in the back and the 2 in the front. That will come into play a little bit later. All right. So we have the blue one way in the front. We have the 2 yellow ones slightly in front. And then we have the 3 red ones just a little bit further back. Okay, so now we're sort of trying to figure out the distances to these objects using the expansion redshift argument. All right, let's take a deeper look at those galaxies. All right, and so we're going to go from fuzzy to clear in both optical and infrared, because this is a ground-based observation from the digitized sky survey. And you can see the galaxies and you can see the details. But if you really want to see the fine details, well, as they say, Hubble got you. All right, invisible light, you get a tremendous improvement by going to the space telescope, going from ground to space, ground to space. And you can see the improvement and why Hubble was such a quantum leap in optical technology when it launched in 1990. Well, we had a similar thing happen. We do have the Spitzer Space Telescope up there, but that has a relatively small mirror for an infrared telescope. Remember, infrared wavelengths are longer than visible light, so you need a larger mirror just to get the same resolution. All right, and Spitzer's mirror was actually smaller than Hubble's, so Spitzer couldn't achieve the same type of resolution Hubble could. However, as we talked about earlier, Webb launched and started producing science a year ago, and from Spitzer, you get the quantum leap to Webb. Yeah, it's the same big jump. Spitzer and Webb. Spitzer and Webb. And you get that amazing jump in resolution that makes the images just pop. I mean, this is what makes the Hubble and Webb images really just speak to you because the resolution just pops and you see all the details that you couldn't see before. Of course, I know what you're thinking. You're going, all right, well, how does Webb compare to Hubble? All right, just remember we're comparing apples to oranges a little bit here because Webb is infrared and Hubble is visible. But of course, I have that for you. So this is Webb and this is Hubble. Webb and Hubble. And Webb and Hubble, okay? All right, Webb, in truth, in looking at this in detail, Webb has about 1.5 times the resolution that Hubble does in these two images. So for every 2 pixels that Hubble sees, Webb sees 3 pixels, okay? And that's an important difference because it gets you just that little bit extra clarity and such. But what is altogether even more important is look at those background galaxies, okay? There's Hubble, all right? And you got some background galaxies, but they're kind of faint, but boom, they pop. Those background galaxies pop in the infrared. And that has been a consistent observation of the, in the images that we've gotten from Webb, is that distant galaxies are really much brighter in infrared than they are in visible. The infrared sees the low mass stars for the nearby things, but as things get shifted into the infrared, those small distant galaxies actually are much brighter. And of course, Webb has technology that's much newer than Hubble's. I mean, Hubble's last refresh in its technology was 2009, and Webb launched in 2021, or at the end of 2021. Or effectively 2022. But anyways, there's a decade or so of technology improvement in Webb. And so this is really, great stuff that's going on here. Okay? So let's take a look at some of those galaxy shapes, and we'll do this sort of the comparison between the infrared and visible, just to sort of get you the basics of it. Okay? So this is NGC 7320. That's that foreground galaxy from Hubble. And what dominates this image are the blue stars here. These are the massive young stars, the newborn stars, okay? The only stars that shine really bright in blue light are the very massive ones, and they don't live very long. They die after 10, 50, most 100 million years, okay? So if you see blue stars like this, you can see there's star formation going on. And that star formation is going on in those pink regions. Those pink little clusters all over the place, those are characteristic of a star-forming spiral galaxy. However, you see none of those in the infrared. This is the Webb image of NGC 7320, and you don't see any blue stars. You don't see those pink star-forming regions. Instead, what do you see? You see those dust lanes, okay? You see the amazing dust that is spread out within the galaxy. I sometimes mix my metaphors and say, this is like taking an X-ray of the galaxy, but X-rays are a totally different wavelength of light, so it kind of confuses things. But the thing of it is we're seeing the backbone, the structure in the dust underneath the stars, because in Hubble, there is that dust is there. That gas and dust is here, but it's brown, and it doesn't emit light. Matter of fact, it absorbs visible light. So if you look at the brown stuff here, and then you go to the Webb image, you can see how it goes from brown to bright. From brown to bright, it now emits in infrared wavelengths. So we can see really the details. The other thing you see is there's this sort of fuzzy, dull thing of stars all over the place. All right, those are the low mass stars. Whereas I talked about those blue stars being the high mass stars, the newborn stars, these stars that we see in infrared are the low mass stars that are spread out all across the galaxy. They aren't defined to the spiral arms. They live for billions and tens of billions of years, so they spread across the entire galaxy. And why is that important? Is because these low mass stars are the dominant types of stars in the universe. If you want to study the generic population of stars in a galaxy, infrared is where you want to be. All right, so Webb sees them much better than Hubble does, because Hubble is dominated by the stars that are bright in visible light, and those, like the ones that catch your attention, are the high mass stars, and you get the low mass stars in infrared. If we look at elliptical galaxies, well, elliptical galaxies are dominated by old stars. There's not much star formation in elliptical galaxies. There's some star formation, but not that much going on. All right, so here is NGC 7317 from Hubble, and since it's low mass stars, it doesn't look that different in Webb, although Webb sees them further out. You can see that Webb has greater sensitivity to them. So there's the Hubble one, and there's the Webb one. And what you see instead is those background galaxies just grab your attention, okay? I mean, look at those galaxies on the left there. They go from being, they're there, but boom, they just they pop out. If you look on the right side, you see those small little orange galaxies in Webb. Where are they? They're there. If you look real close, they're there in the Hubble image. But man, do they pop in the Webb image. Okay, and that's really cool. And I just want to point out one other cool thing is that this star right here, okay, so this image was taken in 2022, right? Yeah, this was taken in 2022. And Hubble's image was taken in like 2006, I think, maybe 2010, I don't know, at least a decade earlier. And you can see that this star is here in the Hubble image, and it pops to there. Bing, bong, bing, bong, bing, bong. Okay, that is what we call proper motion. Okay, that's a nearby star moving across the field during the decade or so in between. And that's kind of cool, such that we see things like that. So there's, if you look in the little details, you can see all sorts of stuff in the background. But I guess the major point is that the elliptical galaxies, they look kind of similar, all right, in these. Other things within Stephan's quintet are really cool things that catch your attention are the tidal distortions in NGC 7319. Okay, now this is a spiral galaxy, and you can see that there's one spiral arm down bottom here that looks, like it's supposed to. But the spiral arms up here look like there's two of them. There's the bar in the middle, and then there's this other thing over here. Well, that is a tidal tail. All right, so I'm going to outline them. You can see that there are a couple spiral arms up top, one spiral arm down bottom, and then there's this tidal tail stretching off to the left. These are distortions, okay? Like those galaxies I discussed earlier, indicative of interactions between galaxies. All right. You can also see that they were there in the Hubble image taken previously, and there are the spiral arms pulled out in NG 7319, as well as a bit of the tidal tail, although Hubble didn't capture the full tidal tail. This actually goes even further, and I'm going to go back to the ground-based image here to show you that there is this, what they call the inner tail. And of course, if there's an inner tail, there must be an outer tail, of course, all right? But the outer tail doesn't show up in this exposure. You have to really deeply overexpose it, all right? And here is a very deep exposure, boom, that goes and sees all the extra mess of material around it, all right? And you can see this outer tail down here, okay? So there's an inner tail from 7319 and the outer tail. And, I'm sure it was confusing to folks early on that the outer tail looks like it's coming from NGC 7320, which you now know is a foreground galaxy, it actually extends on back up to 7319. So both this inner tail and this outer tail are from 7319. And coincidentally, or not so coincidentally actually, they both point towards this galaxy, NGC 7320c. So, what's going on here? Huh? Well, the supposition and the simulations have been done to show that these tidal tails could have been created by a passage of NGC 7320c by NGC 7319. All right, this is the way it appears in the scientific paper. I'm going to rotate it for you, okay, just so that it's in the orientation that I need. So the idea is that NGC 7320c swoops past NG 7319, and in doing so, if all the conditions are right, and they tested about 20 different scenarios in the scientific paper, they can create not one, but two tidal tails, both the inner and the outer tidal tails. And it roughly happened about 400, 500 million years ago. All right, and that's one thing about these galaxy interactions. They're very slow. They take place over hundreds of millions of years. But in this, you get NGC 7320c swooping past NGC 7319 about 500 million years ago to create those tidal tails. So one of the reasons I rotated this is so that I could then compare it to this diagram where I'm plotting things in redshift space. All right, if 7320c swooped past 7319, why is it so far away from it in redshift space? Because this delta here of about 762 kilometers per second, if you're using 70 kilometers per second per megaparsec, would mean it's about 11 megaparsecs, which is about 33 million light years. Okay? So NGC 7320c could not have swooped past 7319 and then swooped out to 33 million light years away in 500 million years. Just not physically possible, okay? Have to be moving at an incredible velocity to do that. So what's going on here? And the answer here is our second part of redshift, which is called Doppler shift. Now, you probably have heard of Doppler shift, okay? A lot of TV stations use Doppler radar to predict the weather, okay? And they're measuring the wind speed motions, okay, via the Doppler effect, okay? And Doppler effect is simply a change in wavelength or change in the measured speed due to the motion of something, okay? So if this galaxy here, I'm just using M100 as an example, were moving away from us, then it would have a Doppler redshift, and that would mean its measured redshift would be larger. If instead it were moving towards us, it would have a negative velocity towards us. It would be called a blue shift, and it would have a smaller measured redshift. Okay? So this is basically very simple, that the motion away from us or motion towards us comes out as a Doppler shift, and change is the measured redshift, either a redshift away or blue shift. But the most important thing to remember here for this piece of redshift is that the measured redshift is a combination of the expansion redshift, the redshift due to the expansion of space, and this motion redshift, the Doppler redshift, which can be positive or negative and could change it, okay? So generally, and for these galaxies of Stephan's quintet, the expansion redshift dominates. That's the larger one. That's going to be around 6,000 for all of these galaxies. But the motion redshift can change it by making it larger or smaller. So we have this a bit of conundrum that if NGC 7320c is supposed to be up here by 7319, but it appears in measured redshift to be here, well, then some of this difference between its location and where its measured redshift is must be due to its motion. So that's one of the I turned that diagram so that it swoops past and comes towards us All right, so that its Doppler motion would be a blue shift, right, which would make it appear to be closer if you just for the measured redshift. Okay, all right. So the motion of the galaxies toward or away from us changes their measured redshift. And I also note that this is also the relative velocities between 7319 and 7320c, and we don't know whether 7319 is moving away or towards us, or 20c is moving away or towards us. It's my supposition here, based upon the computer simulations, that 7320c is moving towards us, and that's what explains its position in its measured redshift. Okay. But now you say to yourself, well, wait a minute, what about 7318b? It's also at this lower measured redshift. Aha! Here is where we go into a high-speed collision. Okay, so if we look at 7319 on the left and 7318b and 7318a on the right, there is this ridge of material here in between them. And in the Hubble image, it is a ridge of star formation. You can see all these star-forming clusters along this ridge here, okay? That is what we see with Hubble. If we go to the infrared image from Webb, we see the same thing. We see this ridge of dust clouds, okay? We see these luminous clouds all along this ridge, okay? But the kicker is really when you look in the X-rays with the Chandra X-ray Observatory, you get a ridge of hot gas. How hot? Well, you need to be 100,000 degrees, 500,000 degrees, 1,000,000 degrees to glow in X-rays. So this is really high energy gas. Okay, so there is a ridge of hot gas here. And so it's not just a hot gas. Astronomers call it the shocked ridge. So this indicates that there is a collision happening, okay? And what they believe is that NGC 7318b is colliding with the gas between the galaxies in Stephan's quintet. It doesn't look like it's colliding directly with 7319. It's not colliding directly with 7318a, and it's certainly not colliding with 7320 because that's way in the foreground, right? But it's colliding with the gas in between the galaxies, what we call the intra-cluster gas or intra-group gas, since this is a group of galaxies. So this galaxy, there's this cloud of material, and this galaxy is coming in, smashing into it, creating this shock ridge and creating that star formation. All right? And so now we've got it that NGC 7318b has this low velocity looking like it's apparently in front of it, but if we've got this shock ridge, it can't be in front, okay? Things smash together, they shock, they stop, okay? So for 7318b, it has to be located up here. It has to be located near 7319 and near 7318. It has to be located up there. Otherwise, you couldn't get the shock ridge. All right. So therefore, there must be this motion. Like I said, I couldn't tell you for sure if 7320c had motion towards us. I surmised it based upon the computer simulation, but I couldn't give you evidence. That shock ridge is distinct evidence that 7318b is back up there, and it is part of the physical group located around 6,600 kilometers per second. So that means that 7318b must be moving at approximately 900 kilometers per second. And you say, well, how fast is that? It's really, really fast for a galaxy, okay? The Milky Way and Andromeda, I showed you that collision earlier, they're approaching each other at about 100 kilometers per second, okay? Relatively slow compared to this. 900 kilometers a second, that's why it's producing these huge X-rays, this whole X-ray shocked ridge here, okay? But again, let me just state, just to give you the full picture, that the motion of the other galaxies is unknown. We have a measured redshift for them, but that measured redshift is always the expansion redshift plus the motion redshift. For 7318b, we have strong evidence to indicate that it's got this motion approximately 900 kilometers per second. The other galaxies, we don't have exact measures of those, so it's all subject to a little bit of fuzziness, okay? And that's what we deal with in groups of galaxies and clusters of galaxies. You see a galaxy, you know it's in the group, but its measured redshift doesn't tell you the whole story. You need to find some other evidence to try and figure out what its motion redshift is to try and really figure out its actual distance, okay? And that's kind of difficult. Now, this high-speed collision has one other really cool and visibly obvious effect, okay? And it's called the bridge. All right, so here is that shocked ridge along here, but this material to the left that sort of flows off of the ridge has been called the bridge. And there's material here. Now, when I first saw this, and for many years, I looked at this material here in front of 7319, okay? And I thought it was part of 7319. And then when we started working on this project, we recognized that this material has to be flowing off of the ridge and in front of 7319, that this material comes from NGC 7318b. All right, so let me outline some of this that I'm looking at here, okay? You've got this flowing material going across here. You've got all these things. And then what I'm going to show you is the Hubble version of this, all right, where you see those same streamlines. They're not as obvious, okay? They're much more obvious in Webb than they are in the Hubble image, in the infrared than in the visible. But in the visible, we see them as dark dust lanes. Why is that important? Because they're dark. They're not glowing. They don't emit anything. You only see them when they're backlit, okay? If you have something that's dark and you put a light behind it, you can see it. If the light's in front of it, you don't see it because it doesn't glow, right? So in this image, the fact that we see the dark dust lanes atop 7319 indicates that 7319 is behind these dust lanes, all right? And so they're backlighting them so that we can see them. All right, and this kind of blew my mind a little bit, a revelation that, all right, material goes into the shock and then streams across to create this material in front of 7319. Because honestly, looking at this Hubble image previously, I had thought, oh, well, those are just dust lanes in 7319. They're part of that galaxy. And yeah, I was wrong, okay? Don't tell my wife I admitted I was wrong. But yeah, I was wrong, okay? And so, of course, we have to justify this, and there are simulations to justify it going through. This is a side view, okay? And this blue galaxy here is a simulated version of 7318b, and it's moving up towards the group. This green one is 7318a. And so 7318b passes by 7318a. They may interact or they may not really sure. That was a variable in the simulation that they weren't able to decide perfectly whether it worked or not. But it could happen. And then here in the second image, it crashes in and creates the big shock and everything, okay? So yeah, the text on the left says the same thing. Approaches from behind, 900 kilometers a second, possible encounter, creates the shock, induces the star formation, and creates the bridge material. So we got this huge high-speed collision, all right? So this is kind of cool. Stephan's Quintet shows us 3 layers of galaxy interactions, okay? First of all, one of the reasons I showed you that movie earlier is to show you that galaxy mergers tend to be things that create ellipticals. So for 7317 and 7318a, which are elliptical shaped, there almost assuredly had to have been mergers that took place billions of years ago, or a billion years ago, to form those galaxies, and now they're in these nice rounded shapes. It takes a while after a merger of things, but there had to have been a lot of mergers to create those. Second layer of galaxy interaction is 7320C swooping past 7319, creating the tidal tails of 7319 and distorting the shape of 7319, getting you all those interesting spiral arms. That happened about 500 million years ago. And then what's currently going on right now is this high-speed galaxy collision to create the shocked ridge and the bridge of material in front of it. And that's really cool. And that's the story that we wanted to tell. All right. And we told it with a visualization. All right. So here I have to bring in the organization that pays my salary as part of my salary. This is NASA's Universe of Learning. It is a collaboration between us here at the Space Telescope Science Institute, folks out at Caltech, IPAC, Jet Propulsion Laboratory, and the Center for Astrophysics, Harvard and Smithsonian. Basically, it's the people who run the missions for Hubble and Webb here. They ran Spitzer at Caltech, IPAC, and they run Chandra up at the Center for Astrophysics. We grouped together and formed this NASA's Universe of Learning, where we're not about any one's mission, Hubble, Webb, Chandra, or Spitzer, but we're actually about all of the different missions, okay? Which is why I'm telling you this multi-wavelength story that covers observations in visible and infrared and X-ray to illustrate that we learn so much more when we use multi-wavelength observations. What I run in this within NASA's Universal Learning is called the AstroViz project. And we want to create these visualizations that help explain the science behind, build better mental models of, and increase interest in astronomical objects. Visualizations are an attractor. They get people interested in science, all right? And I got a great job. I get to create movies that get you interested in the science or make you want to learn more. I'm very much on trying to help you develop a good mental model of what these objects are like in the universe, okay? And we have, whoops, sorry, wrong one, wrong button. Oh, there we go. Come on, try that again. All right, so we have created a number of these visualizations over the years. Upper left, you see the Orion Nebula. We did that in visible and infrared light. In the top middle, we have the Whirlpool Galaxy that we did in visible, and infrared, and X-ray. We did the same 3 wavelengths for the Crab Nebula, top right. We did the Ultra Deep Field that I showed you a little bit of earlier, the Eta Carinae down there. And then the one in the lower right is sort of my placeholder for where I'll put Stephan's Quintet. But this is just a bunch of visualizations that I've done over my years here at Space Telescope. It was actually kind of fun to note that I've done over 50 visualizations in my 22 years here. Yeah, lots of fun. Our latest visualization, the visualization of Stephan's Quintet. And the narration is actually by me.
Deep within the constellation of Pegasus lies a tight grouping of 5 galaxies. Called Stephan's Quintet, this collection showcases different galaxy types and how they can interact in dense environments. Ground-based observations show the galaxy arrangement, and the Hubble Space Telescope captures the fine details. Using infrared light, the Spitzer Space Telescope features cool gas and dust, and the Webb Space Telescope unveils new depth and resolution. The Chandra X-ray Observatory reveals a high energy component both in and between the galaxies. In 3 dimensions, this spiral galaxy is much closer than the other galaxies. The visible light view shows numerous pink star-forming regions and blue young stars. The infrared view highlights the cool gas and dust amid a diffuse collection of older stars. The more distant galaxies are grouped together. These elliptical galaxies are dominated by older stars and have rounded shapes in both infrared and visible light. This barred spiral galaxy has few star-forming regions and some irregular spiral arms. Its core contains an active supermassive black hole. Energetic material around the black hole blazes brightly in X-rays. More distant material shines in infrared light. A tidal tail provides evidence of an interaction with this nearby galaxy. This small spiral is part of the group and passed near the larger barred spiral several 100 million years ago. This galaxy is undergoing a high-speed collision as it crashes into the group from behind. Its shape features distorted spiral arms and stretched out tails with considerable star formation. This X-ray shocked ridge marks where the galaxy is colliding with the dense gas between the galaxies. A bridge of material that extends in front of the barred spiral galaxy can be seen in X-rays. As bright clouds in infrared light and dark clouds in visible light. An encounter with the distant elliptical may have stretched out the spiral before its current chaotic collision. Stephan's quintet shows several types of galaxies, including some with stretched and distorted shapes that highlight interactions within the group. NASA's great observatories provide multi-wavelength observations that enable diverse insights into this complex, compact group.
Okay. Thank you for watching that. This is our visualization for the AstroViz project for last year. You can watch it on YouTube at the Hubble Space Telescope channel. You can download it if you want to use it in your presentations at hubblesite.org and webtelescope.org. And I note that we actually made several versions of it, one with the narration and the text on screen as you just saw, one with just the narration where we include the closed captioning file so people can add their own captions if they want to translate to other languages. And we have a version with narration and audio description, in which we got a professional to write an audio description to fit in between the narration to describe it for those who are visually impaired. We also have the music and the captions available. There was a press release at universeoflearning.org, and when the website finishes undergoing its refurbishment, which it's been going on for a couple months, universeunplugged.org will have resources related to Stephan's quintet. Okay, so I want to finish with one last thing. Let's go back to the It's a Wonderful Life. So next time you're watching it, okay, and you got the whole family together, and you start watching It's a Wonderful Life, and very early on, about a couple minutes in, you'll get to this scene where the angels are talking. And you can pause this and you can go, hey, wait a minute. I want you to recognize that Angel Joseph there in that galaxy and the senior angel there are in that galaxy. Well, one of them's NGC 7320C, 7320, and one of them 7318, and those are separated by a huge amount. The angels are actually talking across 250 million light years of intergalactic space. And then if you're like my family, they'll look at you like, Dad, it's a movie. Let it go. Move on. Thank you all for listening tonight. Let's bring Grant in and we'll take some questions.
Hello.
Hello, Grant. How are you?
All right. So
this is really crazy because I don't know what the questions are. I'm usually watching the chat while I'm listening to the speaker, and I have a preview. But this is cool.
This is a one-man show today. You gotta have help.
That's why you're here.
All right.
Could not
So
do without your help.
I've got one for you, and I'll be honest. I'm gonna present it to you because it is above my head.
Okay.
What was responsible for the Doppler motion of those galaxies on top of the measured gravitational redshift?
Okay.
I believe it was the second you were talking about.
Okay. So it's not a gravitational redshift, it's an expansion redshift. Okay, first of all. Second of all galaxies have some motion through the universe. Okay, gravity pulls them. Like, as I said, Milky Way and Andromeda are being pulled towards each other by their mutual gravity. Okay, so if you have a collection of galaxies in a group or a cluster, then galaxies that form over here are going to get pulled towards it, and they'll have a velocity towards them. Okay, so apparently 7318b was pulled in the way it was formed, had pulled very strongly towards this concentration of galaxies. So one might imagine that 7318a and 7317 being ellipticals, they would have formed a little earlier, right? And while this one was still forming, they create a mass concentration. You've got all this material in between those galaxies. This one is pulled really strongly towards it, and then smashes into it. Okay, so gravity is what's responsible for motions in the universe. Okay, the dark energy and the expansion of the universe, or whatever, is responsible for the expansion motion, apparent motion. And let me just emphasize that is always apparent motion. It's not real motion. Okay, just because the universe is expanding, the galaxies could be standing still, but they are actually moving. So that's why it's the combination of the expansion motion, apparent motion, and the real motion of the galaxies that are moving through the universe.
Gotcha.
It's not an easy concept to get. You got to discuss it a few times, go through it a bunch of times before it really starts to sink in and sit with you.
So basically like removing the speed of expansion from the actual speed of whatever the object is?
Yeah.
Okay.
And the thing is if you just measure redshift, there's no way to decouple the two. Okay. The redshift only measures the total redshift, and you need other evidence to figure out what the peculiar velocity, the real motion, is compared to the expansion apparent velocity.
That is a clarification that I never had. Like, it has to be there, but it just, I like it. Chat's teaching me things today. I like this. All right. When we talk about, this is a more general question, but I like it.
Sure.
When we talk about how far galaxies are away, or celestial objects in general, and you say that they are X light years, which is also X time, we are looking at the previous photons, which means that we are seeing them as they were,
Yep.
not as they are. Is there any known way to see things more currently?
If you want to see something, you want to see the
Other than
Andromeda
looking
galaxy
closer.
as it is today, you would have to jump 2.5 million light years across space so that you're getting its current photons. Because the photons that are leaving Andromeda today won't arrive to us for about 2.5 million years. So yeah, it's just not possible, given current technology. Okay. Um, and it's really fun to think of things because you can sort of think of that, somewhere in the universe, there's a supernova that's gone off and the stars exploded, and that light is currently on its way to us, and it hasn't reached us yet. The news of that supernova is traveling in light waves and will hit us, right? And so you can think of that the information about what's going to happen to these objects is on its way here. It just hasn't got here. It's like, it's still in the Pony Express and it's only gotten as far as Nebraska. It hasn't made it all the way to Baltimore. It's going to take a long time for that to make it to Baltimore.
This may be a subject that we have somebody come talk about, because we get a question about it at least every month, if not every other month.
As I like to say, space and time can warp your mind.
You're not wrong. How do we know that 7318b is coming in from behind the group?
Because the motion velocity that we can is only the line of sight, okay? It's either towards or away. It could be moving sideways. Let me just say that, okay? There could be some unknown component that's sideways. But it is, according to its measured redshift, if that were all just expansion redshift, it would be closer to us, okay? But this galaxy is having a collision. We see the shock ridge. We can see the collision that's happening, which means it can't be closer to us. It has to actually be up near 7319, okay? And that difference is 900 kilometers per second, which we attribute to being a velocity towards us of 900 kilometers per second, okay? In order to have the observations fit together, you can't have that shock ridge and have the galaxy already in front of the shock ridge. All right.
Okay.
I should do that sideways. Here's the shock ridge, okay, and the galaxy has come smashing into it. But the expansion redshift says it's over here. It can't be over here if it's having a collision, so it has to be over here. All right. And so the difference between those is a huge velocity. All right, and that's the only thing that can explain that difference, is that if it has a large velocity. Or if there is some other explanation, I haven't heard it.
All right.
By the way, let me just thank a particular person. Madeline Yatergren did her PhD thesis on Stephan's Quintet, and she was my go-to for asking all these silly questions about things of Stephan's Quintet that I didn't know about, and helping me understand. She did an amazing PhD thesis studying the bridge of material and getting actual spectra of the emission of the elements in there, and determining the different velocities that are seen in the various pieces of the bridge. She was a really great help, and I really want to thank her. I should have thanked her during the talk. I apologize. Her name doesn't appear on the visualization because all errors in the visualization are mine. Okay, I accept full responsibility for any science errors. I don't want people blaming her, but I do want to publicly thank her for lending me her expertise in helping develop these visualizations. Because I do a lot of different visualizations about a lot of different things, and I need experts as my helpers on this. And so on this project, it was Madeline. All right, next question.
All right. This is in regards to gravitational lensing. This was edited, so let me read. Does the gravitational lensing affect any of the background galaxies in what we're seeing?
Okay.
They're saying they don't see any.
All right, so in Stephan's Quintet, there is no gravitational lensing, significant gravitational lensing, okay? In the SMACS 0723 cluster that I showed, there's a tremendous amount of gravitational lensing, okay? You see all those long, streaky, arky things, right? That's gravitational lensing. That is background galaxies whose shapes have been distorted by the gravity of that huge cluster. Okay. As I said, that's a whole nother talk. We've had some talks on gravitational lensing in this series. And generally, it takes a really large cluster of galaxies, 1,000 galaxies together, to create significant gravitational lensing that you can see with the human eye. Okay. There is something called weak lensing, where you don't need quite that concentration of galaxies, and it makes subtle distortions in the shapes of galaxies that can only be measured statistically. You can't measure it for any one galaxy. So weak lensing occurs many places in the universe. Strong gravitational lensing occurs only in these really dense clusters, or in the line of sights towards those clusters, and seeing the galaxies behind those clusters have their shapes distorted.
Gotcha. All right. Reading through.
Okay, no problem. And you're on your own this
I know.
this week, because usually I can help you and go, oh, wasn't that? And I'll pull up the question. Thanks. That's all right, because when you do visualizations, sometimes the visualization just sort of brings it out, and they're like, oh, it answered. But the visualization is supposed to answer a lot of the questions.
That's kind of its whole intent.
Absolutely.
And as a side note, SMAX is still the best acronym we've ever had. Like, hands down. Okay, here's a more general question. What kind of exposure do you generally, like, how long of an exposure time would you have, or how many different actual images would you use to reference for creation of a visualization or something like that?
Okay, so the images that we use for visualizations are the ones that have been processed, generally that have been processed for the press releases. Okay, so that the images of Hubble and Webb and Chandra and Spitzer were standard press release images that we pulled in. To understand the cluster, I go to, as I showed you, many scientific papers. I use all sorts of images that show me the various things. The look of Stephan's quintet in a tremendous number of band passes. We simplified it to show visible, infrared, and X-ray, as if that was all that was. I mean, there are subcategories within the infrared and subcategories within the visible. And ultraviolet doesn't show too tremendous much for Stephan's quintet, but and another really important thing is the spectra. We tend not to share the spectra with the public. The public has not a tremendous love for spectra. I wish they would have a love for spectra, because it's really important. So we're using a tremendous amount of information to create the visualization. But in the end, we have to simplify it to tell a story that the public can follow along and understand. As I said, the visualizations are an attractor. They give you the basics of a story or something, give you a visual hook, and hopefully it can inspire you to want to learn more, to watch other visualizations, to watch other talks about astronomy, and get your brain engaged in exploring the universe. And it's a wonderful job to have.
All right, so clarification to a previous question.
Okay.
Does the quintet lens background galaxies, given their matter distribution? Like, are you seeing lensing from the quintet on things behind it?
Right. I am not seeing. I know of no gravitational lensing due to the quintet. It is a concentration, and I believe that Stephan's quintet is the densest concentration on the sky of galaxies. Somebody called it that, and I was like, are we sure? And they were like, oh yeah, I'm sure. So I'm quoting somebody else. I can't.
Somebody Canadian.
Yeah, sure.
All right.
Sorry, I had to go Fargo on you. But yeah, even something like that, it's only 5 galaxies, all right? Um, and so we don't see any gravitational lensing from that. It's actually fun that, the quintet is actually a quartet, but actually it is a quintet, so maybe you just call it a sextet, right?
Will the Euclid telescope also visit this cluster and do dark matter observations?
Mm. Euclid is going to operate on a much larger a scale than just looking at individual clusters like this. It will look at the very large, massive clusters. It will also look at the weak lensing that I mentioned. Okay,
Gotcha.
Euclid is going to have a fantastic program being able to statistically measure weak lensing to do all that. But Stephan's quintet is not going to be of a target of interest for Euclid.
That section of the sky, but maybe not.
Yes, the whole section of the sky, not that one little region.
Gotcha.
Okay.
All right.
Last one?
Yeah.
Okay.
In Stephen's quintet, is everything around the same relative galactic age, or is there a large disparity between them?
Well, all right. These are all fully formed galaxies, right? That you can see that there's a barred spiral in 7319. Okay, takes time to develop a disk and the barred spiral and everything. Okay, you can see there are elliptical galaxies. Okay, elliptical galaxies do take time to develop, right? Because they generally form through these mergers. So 7317 and 7318A, they've taken some time. 7320, which is the foreground galaxy, boom, you see that's a fully formed spiral galaxy. 7318b, we can't really tell because it's been ripped apart, but it looked like it had good spiral arms before this. Unfortunately, we can't put Humpty Dumpty back together again and see what it looked like before it crashed in. But I'm going to assume it probably was, because you see those spiral arms and then you get the distortions into the ridge and everything. So I think that has to be. So I guess I would say that you can tell that all of these galaxies are several billion years old, okay? Because the Milky Way, it formed about 10 billion years ago, but it really, it takes another 3-5 billion years to settle into a nice, good structure, okay? So I would estimate from my knowledge of galactic development that minimum age of these galaxies is 3 to 5 billion years in terms of when they first, formed to their current size, roughly their current size. Okay, it's another question of when is a galaxy, and when is it just a bunch of stars that are getting together to form a proto-galaxy, right? I mean, we can't really call the Milky Way in its current form until it has a disk, right? But that little seed in the beginning, could have existed 12 billion years ago, right? So that's another thing in terms of timing. Aging galaxies is when do you turn called the 0 point, right? Galaxies develop from these small little nucleus of things that's eventually going to grow into this giant galaxy, and if you use that as a 0 point, everything's started way early, right?
It makes sense. I think that'll finish us up for the chat.
Okay. Fantastic. Thank you, Grant. Oh, I am tired of talking. Thank you all for listening. We will see you next month. Next month, remember, it is our special Web first anniversary edition, August 1st. Yeah, we're excited about that. We here are excited about this. And tomorrow, okay? Tomorrow is the first anniversary of Webs, and I think we got something a little special for you, okay? So pay attention to the news tomorrow.
More than one something.
And thank you for watching. Take care.